Hello, in this video I'm going to go over how to solve a statically indeterminate torsion problem. This time the problem is a composite shaft, so this will just be going over that same process but a composite shaft this time. So we're in metric, 1 meter long shaft. This is viewed from the right, cylindrical shape, an outer material of aluminum and an inner core of steel. The overall outside diameter is 45 millimeters, and the steel inner core has a diameter of 15 millimeters. At 300 millimeters from the left, there is a 1500 Newton meter torque applied in counterclockwise direction. Now remember, this is clamped on both ends, and because of that, when you sum up the moments, you end up having the two unknown reaction torques in the clamps in one equation. So two unknowns, one equation, it's indeterminate. You can't solve that right up front. And as you can see, I already have the polar moments of area calculated out. So let's go ahead and put this into a program, and then we can go through the four-step process. Basically, you do the same exact process as before, but there's a little bit more calculation involved, and you use the same equations as you did earlier with any other determinate composite problem. You just have to do the four-step process with them. So let's go ahead, pull up our program. So it's one segment of uniform geometry. It's composite this time. So length is 1 meter overall, outer diameter 45 millimeters, inner diameter 15 millimeters, outer shear modulus, aluminum, it's 28 gigapascals, so it's 10 to the 9th. The inner shear modulus, steel, 85 gigapascals. Okay, outer moment of inertia. Inner moment of inertia. Okay. Number of torques, there's only one at 300 millimeters from the left. And it is 15,000 Newton meters. Might have said 1,500 before, it's 15,000. And because it's going counterclockwise, it's positive. It's clamped on the left and right. There is no misalignment here. The shaft is not going to twist a certain amount before the clamp on the right kicks in. This is just standard, clamped firmly at both ends. One segment, two sections because of that torque breaking it up. Let's draw that. Okay, so the three main steps. First time, remove the right clamp, solve for the amount of twist. Step 2, remove the right clamp as well as all of the torques. Then you put on a unit torque and then solve for the net elongation. With those two, you can find the reactionary torque in the right clamp, and you can solve it out as a determinate problem. This pop-up just kind of goes over that over again. Okay. So, step 1, analysis of segment 2, or section 2. One thing to note, my notation style is that there are two digits, two sub digits. The first one is the step we're on, and the second one is the section we're looking at. So this is T12, step 1, section 2. So once you remove the right clamp, there's no longer any torque acting on this section. So it just all comes out to 0. So 0 twist. Now we can analyze section 1. And do note that I have the shear calculated out, but we're only looking for twists so far, so we don't really need to worry about that. We just have to calculate what each of the materials' reactionary load is, and then from there you can find the amount of twist. And again, as usual, because the amount of twist is going to be equal for either the outer and inner material have to twist the same amount, then if you wanted to save time, you could just calculate, say, the outer torque and then the outer twist, and that you would know it would be right. So let's go ahead and put this in. .3894, yes. Okay. So now step 2. And notice that step 2, you're finding the net twist, but it just asks for the entire segment all at once. So you have to go through. Here I have analyzing section 2. Remember, this is with right clamp removed, unit load. So here for section 2, I have it all calculated out. Again, we can ignore the stress, and you find that it has a very small amount of twist, but it is just 1 Newton meter. Section 1, same thing, same amount of load, is just 1 Newton meter. However, the length of the section is smaller, so that will affect values. Notice how that doesn't affect the amount of reactionary load in the material. It's just when it comes down to the twist, you involve the length, so that will change it. And then we can sum up the 2 different twists from section 1 and 2. That gets you your net twist, and that's what we're looking for. So let's go ahead and put that in. 8654 to the -5th. Okay. So as you can see, once you finish those 2 steps, then the program automatically calculates out the torque at the right clamp. And then from there you can move on to the final step where you apply that torque at the right clamp, add back in, the other loads, and you can solve it as a determinate problem. But if you're curious about how that torque at the right clamp is calculated, this is the equation, and this is the equation for when you don't have any amount of misalignment or amount of allowed slip, where you take the net twist from step 1 divided by the net twist from step 2 and multiply by -1, and that gives you the reaction of the right clamp following standard sign convention. In this case, that comes out to -4,500 Newton meters. So that means that on the right clamp there is a clockwise reactionary torque of 4,500 Newton meters, which makes sense because you know that intuitively that makes sense because in the, not quite the center, but the torque applied in the middle of the shaft is counterclockwise, so the reaction at both of the clamps should be clockwise to counteract that. So we can move on to our final step. Resolve the entire problem as a determinate problem, applying that torque at the right clamp on the end, and then you can solve it as a determinate problem. And so now the program is going to ask for all of the information, including the shear stress, in which case you're going to have to solve for everything: the outer, the inner, the shear outer, the shear inner, and so on. So let's go ahead and put that in. You can see I just have standard summation of moments. Then you find the amount each of the materials takes up of that load, then the shear stress, and then finally the twist should be equal between the inner and outer material. Let's just do all the outers first because we can see them. And don't forget, when you're putting in the shear stress, it's asking for the magnitude. So even though this is a negative shear stress, it wants the magnitude. So don't put that negative in there. It won't accept it. That is only with the shear stress. You can put in the inner values. And let's check that. Okay, looks good. We can move on to analyzing section 1. Summation of moments. That load applied in the middle far overpowers the load on the right end. So it looks like the reactionary load of the left torque, or the left clamp, is going to be much higher than what's in the right clamp. And intuitively that makes sense because the counterclockwise torque is applied much closer to the left clamp than it is to the right clamp. So let's go ahead and put in these values. Oops, that should be going there. Let's delete that. That's okay. And the twist, 0.2726. Okay. Inner torque, okay, solution complete. And you can see that the net twist comes down to a very small value. We have positive or negative 0.2726, then positive of that, add them together. It should come out close to 0. And that's because the net twist at the far end, it's clamped. It cannot move. So it better come out close to 0. And if you're getting a net twist that comes out to a larger value, then you know that something is up. And you can see the net twist difference between here and what I have written out here. That just comes out to the difference in rounding values. Either way, it's a very, very small number. Should be effectively 0. That's pretty much it. That's all there is really to approaching a composite problem. It's the same 4-step process, 3 or 4 step really, except that you have the extra equations that you have to do in calculating, outer versus inner material and so on. But to save time, you can almost ignore that and just say for the first 2 steps where you're only caring about the amount of twist, you could just stick to calculating just the outer material or just the inner material, and then only calculate out both of them for the very final step.